exam or question 33. A lot of this one is going to come down to definitions. Do you know what your definitions are? Okay, so the first place to start would be electrophilic, okay, which is electron loving. If it is electron loving, we're looking for a positive. Okay, so that as kind of first steps through this question is useful. So we could then go through and say, well, then the oxygen is going to be our most electron loving because it is positive. But if we check, its octet is satisfied, and if we were to go through and say, well, if a nucleophile came in, we would exceed that octet, what would we have to kick out? Well, we'd be kicking out hydrogen, carbon, or carbon. Are any of those good options to actually accept the electrons? No. So that step actually makes no sense. The oxygen can't act as an electrophile. So zeroing in on the positive charge may then be like, well, then what am I supposed to do if I can't look at the positive? You can look at the positive. You just have to address how that affects the overall structure. The oxygen does not want to be positive, so it is withdrawing electrons from within the structure. As it withdraws electrons from within the structure, that's where we're generating our other potential reactivities, or where our reactivity is going to fall. So the next most common answer that came out would be that hydrogen. So we're having this nucleophile come in, share electrons with that hydrogen. Because that hydrogen now accepted electrons, it must have therefore been an electrophile. Okay? This is where having the definition on our electrophile nuanced very, very carefully. The electrophile was electron loving in that it accepted electrons, but the thing that accepted the electrons was not hydrogen. Because if it was hydrogen, it's not an electrophile, it's an acid. Okay? So the hydrogen is not an electrophilic atom here, or not the electrophilic atom. What it is in this case is an acid. And so that doesn't satisfy this question. So the oxygen's out, the hydrogen's out, which then leaves us with that last carbon, which could make a decent amount of sense. Okay? If a nucleophile came in and reacted with that carbon, then it would really be a nucleophile electrophile system, not the acid-base system. Whoops, and if we color code a little better, not the acid-base system that we've got running in the other situation. Okay? The last answer that people usually pick as they think about electrophiles, and they go, oh, halogens are great, are associated with electrophiles. And yes, they are associated with electrophiles. The carbon where the bromine is connected is electrophilic. You'll also notice that that atom was not specified in the list because that would be a confusing one to nuance out between those two carbons, where the oxygen's connected or where the bromine's connected. Okay, so the bromine itself is not electrophilic. The carbon where the bromine is connected is electrophilic. Okay, that's where a nucleophile would attack. So this question is really trying to push at how do we differentiate electrophiles versus, or electrophile nucleophiles versus acids and bases. Before I start deleting any of that work, does anybody want to chime in with a question? Oh man. And I was going to say you can't chat because it won't pop up on my screen, but then Garrett's comment very quickly jumped up and now I can't see it. So if I'm going to go through and adjust this to see what you guys are asking, I'm going to lose all this work. As long as you're okay with that, I'm okay with it.
I think he asked the same thing that I did, but maybe not. I wanted to know, based on, I thought on the practice test, that it said that it was the hydrogen.
To reference the practice test, I'd have to jump out of this.
Yeah, I'm trying to go find it. But I think that's what he was referencing also, was
recording. I'm asking you to go through and apply what you recognize before and after a reaction to try and predict what kind of reaction has happened. So if we look at this, it's saying for step 1, so the first thing we should do is put on some selective vision and delete step 2. And we want to know what the aldehyde, so we're identifying our aldehyde, what the aldehyde acts as in step 1. So there might be some pieces that are odd here. You might notice that there's a 2. So really what that's saying is that we have 2 of these. So if we write this out, and I'm not going to show lone pairs, this is what we're looking at. So if we compare across, these 2 are the same, which means nothing happened to them, so I'm going to ignore them. So something had to happen between, we'll call that our ethoxide and our starting aldehyde. So what changed between the starting aldehyde and the product? Okay, well, that could be difficult to see if you aren't used to what we talked about back in Unit 1 on when you imply hydrogens. When we go through and compare this out, what changed to that aldehyde structure? A hydrogen was removed from it. Okay? So we're talking about the loss of a hydrogen. Before we get too excited about it, we do also want to go through and address what characteristic of the hydrogen, or what is the characteristic of the hydrogen that was lost? Our starting structure was neutral, and it ended charged, and in particular, it ended with a negative charge, which means that hydrogen that we lost was H+. Okay? Well, if that compound loses H+, something else had to gain H+, so our ethoxide gained H+. Okay? So based off of our definitions, what kind of a species loses H+, what kind of species gains H+? The species that loses H+ would be an acid. A species that gains H+ would be a base. Which means if we're looking at the aldehyde, our answer here is the aldehyde acted as an acid. And I'm mildly freaking out that the answer was identified as a base, but I honestly don't know. It should have been identified as an acid. And I'm going to pause the recording. Or do you have questions in particular about what we just walked through? Okay. So this was a commonly missed one. This is also one of the most difficult questions, I would argue, in all of the ACS questions for this semester. Because this question brings in pretty much everything. So, where does it start? Okay, it starts because what we're doing is we're trying to think backwards. Okay, so we know that this is the product, and we're being asked to figure out what the reactant was. Okay, so we have to think backwards for this question. That makes it challenging. Not only that, but we also have to know what the reaction was. Okay, to help with that, we can look at our answer choices and see what we're starting with, and we can compare that to what we're ending with, and hopefully what we see is that we have the formation of a pi bond, so we're doing an elimination reaction. Okay, what kind of elimination are we doing? This is where reading the question comes into play. We're looking at a strong. As soon as you see the word strong, you should be thinking 2 or bimolecular. I'm not going to write out molecular, close enough. So we're looking at an E2 mechanism. Now that we know what kind of reaction we're running, the complication of an E2 is that you have to be anti-periplanar. Okay, planar. In everybody's favorite Newman projection, what they're referencing is that your leaving group, in this case the bromine, okay, as I try and identify these pieces as we go through it, needs to be anti to the hydrogen that is removed by our base. So our base has to come in and remove from here so that we can make the pi bond. Okay? And if we looked at the back atoms, okay, stuff is at those positions. So it is referencing this viewpoint on the molecule. That viewpoint is difficult to get into, and you'll note that it was not drawn in that configuration to begin with. Okay, so we have to do some interpretations. One of the things that was done kind of nicely for you is that if we take this Newman projection and we grab that front atom and we kind of pull it, because it's in front of the plane, pull it and move it sideways, what we're looking at is our leaving group being down here, our rest of our structure, and then our hydrogen up here. And then we've got kind of our, as I quickly draw through and do this, our wedges and our dashes. So hopefully that much kind of makes sense as you go through and process those pieces. Okay, so we need to ensure that we have this kind of proper alignment for the elimination. Because it's an E2, it all happens at the same instant, so we're getting simultaneous, which means the orientation of, we'll call it red to red and blue to blue, are locked. Okay, so our relative positions, or our relative substituent positions, are locked. Okay, and they're locked from that anti-alignment. Okay, so with all of that information, now let's go back and try and tackle those potential answer choices. Hopefully what you can go through and see is that these are already drawn in that configuration. And we might say, well, cool, that's nice. They did something cool for us. Before we get too excited about it being nice, we do have to realize that it's a test and not everything's going to be nice. Okay, so let's go through and run this. Oh, dang. Nikes. Okay, I'm going to have to delete everything because I think there was a typo that I fixed and did not fix in the actual draft. So I'm going to have to go back and actually look at the exam. So I deleted all that work, I know. I'm more irritated than you are. Now I gotta find the question. Because I think the answer choice, I ended up having to switch. Oh, and of course everything's shuffled. There. And you're not going to show me the pictures, are you? Thank you, because that would have been freaking helpful. So now you get to see all the back end. Ignore the man behind the mask. Picture, one of those things. And so the reason why I'm jumping out of this system is that if you looked at those structures in the practice exam, they're identical. There is no difference between them. And that was something that I caught as a typo, I think, before it went live. Yes. Because when you look at the actual question, ta-da, it's not the same structure. Okay? And you're also seeing the answer. And if you go back and look at the video, you might be able to scroll through and see what the specific answers were. Lucky you. Okay? So let's go through and take a look. There's the alignment, there's the alignment. So both of these match that ultimate alignment. Okay? So let's go through and run the reaction. For this first one, if we went through and did that elimination, we'd have the phenyl wedged, methyl dashed, pi bond, methyl dashed, hydrogen wedged, right? If we turned that up on its side so that it matches a little bit better, we'd see this. And we'd be like, that is not that answer. So it can't possibly be that answer choice, so that one must be wrong. I know you can see the answer. Hold your breath. Don't hold your breath. I don't want you passing out. Okay? If we look at the other one and we run the elimination, we run this same process. There's our pH. Whoops. There's our CH3, CH3, hydrogen, wedged. We turn that on its side, pH, H, and we'd be like, isn't that the answer? Yes. Okay, that is indeed the answer. So yes, that is valid, and that is 90% of the class that, well, I'm spitting out numbers that I shouldn't be spitting out. The vast majority of people picked this as a valid answer, because yes, it is a valid answer. Both of the structures are valid though, okay? And for those of you looking at the screen and being like, dude, you literally said that the first one wasn't right. I said the elimination of that hydrogen with that bromine is not right. That compound has the full ability to do a sigma bond rotation to bring this hydrogen into the anti-alignment. If that hydrogen is now rotated up, what happens to that CH3? And when we run through that product, we would end up seeing that it does indeed form the exact same valid answer. Both structures could produce the product shown. Okay? Both are potential valid systems. We have to realize that we can do sigma rotations at any point through a reaction. Just because a structure is drawn one way does not mean that's the way it's going to react. It could continue to do other manipulations and permutations to cause things to shift off to get those other kind of products popping up. Okay, this is where being very careful with the wording also comes into play. This is could produce. Okay, both of these could produce those products. Okay, the second one in this particular case, the red one, absolutely would form it in a higher yield. It's not asking that. It's saying which of them are possible to be produced, and both are valid. Okay, this is an exceptionally challenging question. Again, I would argue the hardest on the test. It requires the combination of a whole bunch of different content areas from the semester. Okay, so if you got this one wrong, but because you said, what was that, the red one, you should count that as a win. That's good. Okay, and what you're missing is just that next level step, and that's what this question is. It is a next level question. Okay, questions about that one? Okay, I did just see it minutes in the video. When we're looking at 37, trying to process through all of this to decide what's going on, one of the things that I would go through, personally do first, is that when I see this structure, I'm acknowledging it as secondary. I'm seeing this and I'm seeing strong. Aprotic and elimination. That little delta symbol means heat. High probability we're doing an elimination. Okay. Conclusions that get drawn from each of these things. Secondary, skip it. Okay, skip the question. Why? It's secondary. Everything can happen with a secondary. Substitution, SN1, SN2, E1, E2. It's going to be a hard question, okay? So you're going to have to nuance a lot of details if you're seeing a secondary substrate pop up. That presence of that sodium immediately means strong. Because it is strong, we're looking at that 2 type or bimolecular, which means we're looking at SN2 or E2. The aprotic solvent, okay, misleading. So it's usually something I leave alone. And then that heat, I already wrote the conclusion that it's an elimination reaction. So based off of all that information, I would direct immediately towards the elimination reaction. If I'm going to eliminate, where's the best place to eliminate? We've got a hydrogen here or a hydrogen here. I want to eliminate to form the most substituted potential product. So I'm going to eliminate in the case on the blue side because I'm going to get a more substituted pi bond. Okay? That then drops me to answer choice D, which is the correct answer. I am fully admittedly am going to freak out a little bit here because when I go back and look at all of my answer choices together, 3 out of the 4 of them show substitution. Okay? And if I was going to look at just kind of test building, I might be like, well, I want to have enough distracting answers. So substitution might be a better working through on the guess. So I am going to panic with that a little bit. But unfortunately, those distractors are there for a reason. They could easily be messing with you. If I really wanted to push into this a little bit further, it could be like, that one has to happen with a rearrangement, which would mean in SN1, I have evidence that it is not SN1. Okay, so as a distractor, that's a very, very bad distractor. Same deal with B, also a rearrangement. So if I do that, I'm now looking at boiling it down between 2 answers, substitution or elimination. The heat is a tip-off that I'm probably doing the elimination. And as unfortunate as that is, that's really heat's role, is to really kind of push the elimination over the substitution. Questions on that? I don't think I saw anything pop up. So question 24. How do we decide what's going on with this? SN1 mechanism. As soon as I see the word SN1, I'm going to be thinking carbocations. In the process of the formation of a carbocation, we may see other things going on with it, but that is at least a big red flag for me. So I would be jumping immediately to these 3 answers as a possibility. In answer choice B, those electrons are moving into a bond. So we're looking at the formation of a pi bond. Formation of a pi bond is an elimination. This said substitution, which means B is wrong. In C, same deal. We're shuttling those electrons into a pi bond. Form of pi bond, elimination, also wrong. In D, we're having a negative bromine come into that positive. Yeah, that seems reasonable. Okay, that's looking at a coordination mechanism, which is the last step of a substitution and of a SN1 in particular mechanism. So yeah, that's valid. I did only eliminate B and C, so I should go back and take a look at A just in case there's something weird there. We're taking the electrons from iodine and we're putting them on carbon. That says the electrons are going away from the most electronegative element. That's also wrong. This is actually an invalid mechanistic step. The electrons are actually moving inappropriately. B and C are both valid mechanistic steps, but they're definitely elimination reactions. B is in E1 and C is in E2. You were asked to do an SN1 reaction in this case. D is the only one that is a valid step within an SN1. Questions on that one? 9 seconds. So if we are looking at the carbocation most likely formed when this structure undergoes rearrangement. So we've got a carbocation. We need to do a rearrangement. That means we're moving an atom from somewhere next door. So we could do this as a rearrangement. The result of that would be that we now have the 2 hydrogens there, and we now have a positive charge out there. This would be a primary carbocation as opposed to the secondary we started with. Our rearrangements only go in the direction of more stable. So that is actually an invalid rearrangement. C is not going to happen, which means also that D isn't valid. So we're really only looking at A and B. So now the question is, what should we do? Okay, how do we get either A or B? Okay, and this is one that becomes a challenging one for students to see. So I'm going to look at B first, because B is usually easier for people to see. When we go through and do that rearrangement, we're taking that hydrogen, we're doing that rearrangement across, which then means we've got our ring still. There's our carbon with now its 2 hydrogens. We still have that CH3 with nothing on it, and we'd have that positive charge and be like, well, that's exactly that rearrangement. Okay, we started as a secondary and we ended as a tertiary. Isn't that a valid rearrangement? Yes, that is absolutely a valid rearrangement. Is it the most likely rearrangement? Okay, if we're going to make the statement that it is a tertiary and it is therefore more likely to happen, then we should use that same argument for A, and A is also tertiary. Okay, so maybe the argument that students made, and this is standard, this is kind of typically what students will go through and make on this, is what the F? There's no way that that could possibly happen. Okay, well, let's go back and look at our differences to see if we can establish what the relationship is between these. Because most people go through and see a 5-carbon ring versus a 6-carbon ring and say, well, that's just a bad answer choice because it's the wrong thing. Okay, before we start getting too excited in that, that's where it's helpful to go through and reference formulas to decide what is the relationship between those. And if we go through and look at the formulas between these, this is C7H 3, 4, 5, 6, 7, 8, 9, 10, 13. I think I did that right. C7H13. If we look at the next one down, 6 carbons, 7 carbons, 2, 4, 6, 8, 10, H13. They have identical chemical formulas. These are isomers. We didn't change really anything except we rearranged where atoms were located. Well, was that rearrangement possible? Could we have done that? Well, instead of moving, say, a hydrogen, let's go through and move a carbon. Same process. I'm going to take these electrons and I'm going to move them to here. Okay? What does that mean happens to the bond that was in there? Okay, well, now that bond no longer exists. Those electrons are now in the bond with that other carbon. Okay? So what does that mean happen to now our purple carbon? Well, that purple carbon has now lost electrons. Oh! What's going on? I think I found a typo, so it looks like we can get some points back on this. That purple carbon, yeah. I know I found a typo. So we can definitely get points back on this. Becomes a carbocation. And if we rearrange that structure out, what we end up getting is our 6-membered ring with a carbocation. I didn't find a typo. Sorry. Oh, I gave points anyway, so it's okay, actually. And we might be like, okay, well, there we go. We'd have a secondary carbocation. Well, which one should we form? The secondary carbocation or B, the tertiary? Turns out the secondary is actually more stable in this case because we've gone from a 5-membered ring to a 6-membered ring, and 6-membered rings are more stable than our 5-membered rings. What can now happen? Yet another rearrangement. And we now move to a tertiary with 6-membered ring. Everything about A is actually going to be the most favorable result. Okay. Typically where this question ends, I hear someone about to come in with a question. That's okay. Give me a sec. Typically where this question ends is actually with this one. So you would see that red structure subbed in there as your answer choice. In fact, I think that's in the study guide, the ACS study guide for rearrangement. This is a very common ACS style question. Someone was chiming in.
So if we did put that as answer, but it was marked wrong, are you saying that we got it?
Yeah, both A and B were accepted as valid answers. A was the correct keyed one, and then B you should be seeing as regraded. And I can't show you that, but it should show up on your screen in your canvas as regraded. And if you said B, you should be seeing 1 out of 1.
Okay. Yeah, all I see is that it says I missed it, but I should have got that right.
So, because it involves grades, 6. So, optically inactive, we'd be looking at losing stereochemistry. So, hopefully what we had memorized for loss of stereochemistry would be an SN1 mechanism. So, before we actually do anything else, since we know we're looking at a solvent, and we know we're looking for SN1, the solvent that supports SN1 should be polar protic, if I could spell that correctly. Okay, to be protic, we're looking at a hydrogen bound to nitrogen, oxygen, or fluorine. Okay, which could be another layer on this question. Then we're given the reaction with a box shown below it, which ultimately really doesn't matter. It doesn't matter in this particular question. No, it does matter. So we do have to be a little bit careful with saying it's SN1 from being optically inactive. So I kind of spoke a little too fast on that. Optically inactive is likely to be SN1 because that's when we lose optical activity. But if we didn't start with optical activity, we aren't going to end with it either, and either mechanism would have been okay. Okay, so hopefully that makes sense. So we do need to actually look at the reaction to see what we're starting with. And since we are indeed starting with optical activity and then losing it, that means SN2 is not valid. Okay. We could also add to that when we look at the overall reaction, what happens? The bromine versus the nucleophile that came in have changed positions. Okay, that change in positions is going to suggest a rearrangement, which is another red flag that we're looking at an SN1 mechanism. Okay, again, SN1, we should be pushing for polar protic. So we then go to our answer choices. In this case, we weren't even being given structures to evaluate. We were just told the list of possible names, and we've got polar protic. Okay, if you're in a situation where you're like, holy crap, that's a lot of information to process, you could just go based off of definitions. If you're non-polar, by definition, you will be apolar aprotic, which means both of those are wrong. You're now down to 50-50. Okay. Questions about that one? Stability for radicals. A couple people commented that they were freaked out that radicals showed up on this. We've addressed stability of radicals. Radicals are carbocations as far as their reactivity goes. So all you have to do is change these to carbocations and now evaluate. Okay, and trying to decide stabilities. Because we're looking at stability, we would want to go through and look at all of that rankings that we've addressed before in the past. What this is going to come down to is there really isn't any difference between these except that they are carbons, so we're looking at substitution and potentially hybridization effects. So we're digging kind of deep. So we would start by labeling these out: secondary, tertiary. One becomes very challenging to label. It is not secondary. That primary, secondary, tertiary organizational system only goes towards sp3 atoms. That's not an sp3 atom, so an sp3 type, so single bonds only. Because it is directly connected to the pi bond, that one actually gets labeled as sp2. sp2 carbocations do not exist. Okay, we cannot form those, at least as far as this semester goes. Because we cannot form that, we already know which one is now our least stable. One has to be the least stable. So now the question is really going to come in, because of course we now have B and C that we have to organize, and the only difference between those is how we organize that tertiary versus that secondary. Well, as we all know, tertiary are more stable than secondary carbocations, so we might go through and say that C has to be our answer. And you're probably asking this question because you got it wrong. Okay? Tertiary are more stable than secondary. However, that is not just a secondary. That is a secondary plus resonance. The resonance overwhelmingly stabilizes our carbocations much more so than a substitution effect. Remember, when you're thinking about the substitution effect, it's how much electrons there are nearby that don't directly share, that are just nearby. Resonance is there's actually electrons coming in to stabilize. So resonance is a much larger effect than substitution, which means 3 is our most stable, followed by 2, followed by 1. Maybe there was a chime in there. Did I hear a click? Are there other questions with that one? Triple. Starting from an alkyl halide, in fact a dihalide, the first product. I'm going to just accept that. Was this what I wanted? This structure ends up being exceptionally unstable. Okay, and to get that last step to happen, to get your final, what reaction am I thinking of? I'm thinking of the reverse, I think. Yes. Sorry. That's what happens when you try and think of stuff on the fly. If we add HBr, oops, and we do that twice, this reaction is exceptionally slow. That's why I'm struggling with this. This is in our next section of material, which is why it doesn't make direct sense to you right now. I apologize. This is in the next section of material. Alkynes will react with acids or electrophiles twice, just like an alkene would, because they are pi bonds. But this reaction is very, very, very slow because one of the intermediates that's formed is a carbocation. And in particular, our carbocation on an sp2 carbon. Due to the extreme instability of that, I think that's right. This first step is very, 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 very slow. Okay, so the carbocation is exceptionally unstable and it doesn't form well. The only reason we get the reaction to work is that we give it lots of time and plenty of heat to kind of overcome some of that stability issue. So if we look at it in just straight substitutions, it's so incredibly unstable, it just does not form reasonably. I did get a complaint about this question. You can fully expect something along these lines for your final as well. I do actually remember one year there being a brutal question about it someplace that, because I'm recording, I shouldn't mention. Yeah, that was an interesting one. Any case, for this question, what we have to go through and do is kind of process out our reaction. So we're looking at an acid catalyzed unimolecular elimination. So we're referencing an E1 in the presence of H plus for the structure 2-methylcyclohexanol. One of the things when trying to draw out your structures as you're thinking about these things would be to try and match where the relative positions are according to your drawings out here. So while you could have drawn this cyclohexanol and OH and like that, okay, that is perfectly valid. There's nothing wrong with that. The closest you can match your answer choices, the better off you'll be, because you'll have to do less permutations later on. Okay, so just something to consider. So the major complaint that comes with this question is that you have to process through all of the mechanistic steps. And yes, you do. That's what happens with a reaction like this. So we could start it off and say the most reactive thing would be our H+. We need to neutralize that H+, which means the oxygen needs to react with it. So we now have a good leaving group. Because we're told this is an E1, we know we need to form a carbocation. Totally going to run out of space drawing all this, which means I need to have that leaving group. So there's a carbocation. As soon as I have a carbocation, I should be considering rearrangements. Once I've now got my stable carbocation, I can now finish my elimination. The elimination, particularly in E1, is driven based off of stability. We're going to get an internal pi bond. So we've got 1, 2, 3, 4, 5 structures, starting with A, B, C, D, E. Fascinating, that happened to match the perfect alignment shown above. If we missed any of those steps along the way, say the rearrangement, or even that acid-base step, we wouldn't be able to match this out nicely. And that's one of the reasons why a question like this does show up, is because you really have to understand the entire mechanism beginning to end. So is it something that people can work their way through, or have they just memorized the content for the class? Okay, and so that's why this kind of question is a common one to show up for something like this. So if we now go through and just kind of process this out, we're looking at position D on that. So 1, 2, 3, 4, D, there's the carbocation. Our answer comes in as B. If we didn't have all of the knowledge to go through and process that, is there some stuff that we could do to kind of eliminate answer choices? Okay, this is looking at point D, which is not the beginning, it is not the end of our reaction. which means it must be an intermediate, which means charged is very, very, very likely. Okay, which means D is wrong. Okay, we should also, well, we could just do that. Okay, so that's why D is out. If we go through and look at A, B, and C, all of those as answer choices match intermediates within our mechanism. It's recognizing when those individual steps happen that become the important aspect. And yeah, if you understand the chemistry well, you should be able to predict out that mechanism quickly. If you don't, it will take more time, and that's one of the reasons or ways that we can nuance how well students understand the material. Okay? As unfortunate as that may be, that's a real result of this. Questions about what's shown up there? I don't know if I set a time, but I know I'm at 45:50 right now, so maybe 40 minutes. And in E1, the leaving group leaves first. Oops. Leaving behind a carbocation. So we get the heterolysis. And then you get the elimination step, where your hydrogen is removed to form the pi bond. And this is where I disagree with Carty's labeling, but he calls this electrophile or electrophilic elimination. And I think he should be calling it an acid elimination. If we look at an E2, an E2 is that those two mechanistic steps happen all at one time, simultaneously. Formation of the pi bond and ejection of the leaving group. This is known as an E2 mechanism. And you end with that. So in E2, we run it all at once. In E1, we break it into multiple steps. Kind of like SN1 and SN2. In SN2, we do the substitution all at once. In SN1, we break it up into individual steps. So it's the same overall process. So, strongest nucleophile at 4728. So strong, we're looking for negative. Nucleophile is nucleus loving. Okay, a nucleus is positive, so if we're positive loving, we're looking for a negative. Strong doesn't necessarily mean negative, strong means charged. That's really what I should be referencing there. So if we're looking for a strong nucleophile, we're looking for something that is negative. So if we compare A and B, that should be an easy pairing to get rid of. We get rid of A, we can look at C and D, and we can get rid of C. And so we're now left between B and D. If we're looking at ranking nucleophile strength, we usually get people jumping all over oxygen. Okay, and well, how are people referencing it as oxygen? So this is where going through the rules of reactivity come into play. We start with charge. Okay, strongest nucleophile, we start with charge. If it's negatively charged, that matches nucleophilic characteristics. Both B and C are negatively charged. So then we move to 2, and we move to size. What are we comparing in size? We're comparing carbon to oxygen. They're both in the same row. There's no change, so size is irrelevant. So then we move to electronegativity. Okay, oxygen is more electronegative. Okay, what does it mean if it is more electronegative? It holds the electrons. What must a nucleophile do? Okay, and so the reason why people say oxygen or D as your answer is being most nucleophilic is they go, oh, oxygen's more electronegative, so it will get electrons more often than carbon will. That is absolutely true. Both of them already have those electrons. you're making a comparison at the wrong stage in the game. The comparison here is they already have those electrons. Okay? This isn't them trying to become negative. They are already negative. Okay? So this was one that very commonly people put oxygen, and I think it's coming from oxygen is more likely to be negative. Irrelevant to the question. Both of those atoms are negative. Okay? Once they are both negative, you then have to evaluate their abilities as far as nucleophilic characteristics. Questions on that one? So 5025. For a reaction, what happens to the rate if the solvent concentration is doubled? One of the reasons why this question, or there's a couple reasons why this question becomes tricky. It is also an incredibly common question. First and foremost, they don't show you a rate law. So you have to remember what a rate law looks like, which is fun because that's 152 content and nobody liked 152. So everybody gets it wrong because you don't even know where to start. Okay. We now add to that layer or add to that complexity by now looking at a rate law, and we get these brackets. What do those brackets mean? Concentration. Well, how do you measure concentration? It's the amount of solute, and in particular, in chemistry, it's the moles of solute divided by the liters of solvent. Why does that become important? If I double the solvent, what happens to this rate expression? Ignore question 20 for the moment. Okay. If I double the solvent, my denominator gets twice as large. For that particular rate, it would go in half. Slow the reaction by half. Okay? So that solvent has a very sneaky role, and it kind of comes in on the back end of understanding what our rate laws are and what those symbols mean. Why does this become extra, or not necessarily extra challenging? If we go back and look at the question itself, it now says for an SN2 reaction, okay, for an SN2 reaction, the 2 is there because when we look at the rate law, it's the concentration of your substrate times the concentration of the nucleophile. There are 2 pieces, and that's why it's SN2. Those were both concentrations. So if I look at the concentration of the substrate, it's our solute over now twice the solvent. If I look at the concentration of the nucleophile, it's the nucleophile over twice the solvent. When I double the solvent, that doubling shows up twice. And we end up getting a net result of quartering the rate. So our rate quarters, and we get D. So you've got to be careful on what things show up in your rate law and when they show up. If you know 152 is a weakness, you may just accept it and memorize what you can. When you see it, just throw down an answer and move on. Questions on that one?
So you said the substrate and the nucleophile may break down and become solute.
I wrote it as solute. I really shouldn't have written it as solute. That would still be the substrate.
Oh, okay.
Yeah.
Okay, now. Yeah, because it's 1/2, right?
Yep. So question 3 is a spectroscopy question. For better or worse, because I absolutely control the exam, it will make up 10% of your exam. So you should expect 7 questions on spectroscopy. That does not mean they're all like this. but you should be expecting a question like this, particularly because this was a very commonly missed question. Time is 54:48. So, in processing through this, I immediately jumped to that being a singlet, which means 0 neighbors. It's also very tall. And if it's tall, it should be lots of hydrogens. Okay. This question was put on in this format, just to give you a little bit of background, because it's typically how the ACS has been formatting spectroscopy questions. I disagree with that format because I now have control over the absolute final. You will see integration information specified on this. So you would see that that was a 3 hydrogen signal. Okay, just for the record. You didn't have that, so let's go ahead and delete that. So we're looking for 0 neighbors, lots of hydrogens, because it's tall. If we go through and look at A, every single one of those has hydrogen neighbors, so A doesn't make sense. B, that guy right there, has 0 hydrogen neighbors. C, we might eliminate on the outright or outset, but you gotta be careful. You gotta watch out for that hydrogen of the aldehyde that's chilling out there. And then D, we have that hydrogen with no neighbors. Okay. It's tall, so lots of hydrogens. That would suggest both C and D are wrong just based off of that integration information, which leaves us with A, and we'd be done. We'd also be correct. Okay. If that didn't work for us, what else could we try and pull from? The aldehyde hydrogen is a very specific hydrogen that shows up at 10 ppm. If we go through and look at our range, we're looking at 3 to 0. That doesn't show the aldehyde hydrogen. C is wrong. The blue hydrogen for our carboxylic acid, also a very specific hydrogen that shows up about 12 ppms. We're not in that range, also wrong. Okay, so with those pieces of information, it really only whittles you down to B being the only potential answer. We could get nervous and be like, well, maybe we've overanalyzed that single data point by only looking at that as a single peak. Okay, that's fine. If you've got the time, then address the rest. Okay, we're looking at a small peak with 2 neighbors, and then lots of neighbors. A has lots of neighbors, so that's possible. If we go through, we have 2 things with 2 neighbors. This guy has 2 neighbors. This guy has, whoops, gotta be careful with that one. This guy has 2 neighbors. This guy has lots and lots. Okay, so that seems to match. If we looked at the first one, answer choice A, that one has 2 neighbors. This one has lots. This one has lots. This one has only 2. Okay, so these 2 could, God, that looks awful. Give me a sec. We could try and make the argument that those are those 2 neighbors. Okay, we could then also go through and say, well, maybe this is just a big convoluted mess in there. Fair, but now how would you explain this remaining peak? Okay, that then doesn't make sense. So again, the answer here really only comes out as B as being the only potential standout. The easiest way for me to go through and process is as I went through and did, is look for those things that require minimal interpretations. A singlet, 0 neighbors, that's a really big, easy thing to kind of jump on and look for things that match that and then whittle down your answer choices from there. Questions on that? Where does the double bond carbon to oxygen show up? Give you a hint. It's 200 ppms. And it shows up in carbon NMR. Which spectra were you given? You were given a hydrogen NMR. That's why you didn't see it. What you might be considering is more that aldehyde hydrogen, that if you have a hydrogen connected to the carbon of a carbonyl, that shows up at 10 ppms. And you're right, that didn't show up. That's why we could eliminate C. Right? If we look at the carbonyl with one atom further away, that hydrogen does show up in your HNMR. It shows up at 2.1. You might wonder why I know the specifics of why it shows up at 2.1 ppms. That's because I've gotten that question wrong multiple times. Multiple freaking times. The hydrogen that is, if you want to get into the nomenclature that would show up in second semester, that is beta to a carbonyl shows up at 2.1 ppms. Every single time. It's freaking stupidly precise. Yes, 41. Yay, 41. Times 6105. 41 is ultimately where OChem 2 goes. Okay, so that's kind of your end goal. And it is one of the harder aspects of organic chemistry. What you're trying to do is, or what we're doing in OChem is learning the reagents. Eventually, what we want to do is string reagents together. We don't care that adding iodide acts as a nucleophile and we can do a single substitution. We care, what does that allow me to do 10 steps further on down the road. Okay? So when we're looking at OChem right now, all you're looking at are what are the basic pieces. Now what we got to start thinking about is how do you string those pieces together. This is why OChem 2 becomes so hard, because the big aspect, or a big aspect, probably 10 to 20% of every exam in OChem 2 is now string together multiple reactions. So you have to be thinking about your reactions in that sense. So in 41, we would start with our very first reaction and trying to identify that reactivity. Hopefully we see that as NH2 minus. We can drop the metal. Since it's NH2 minus, we're looking at that as a strong, now nucleophile or base. If it acts as a nucleophile, then that means our starting material must act as an electrophile. Those two positions would be our electrophilic positions. Okay? So we could be like, well, we've been studying substitution with nucleophiles, so maybe that's the route we should go. If we went through and did that, we would react at both of those positions, and that would get rid of 2 NH2s. This says 3. That 3 is a hint, it's a tip-off to try and help guide you on this, because you're new to our substitution and ultimately our full synthesis. So what's going on with that third one? You could try and make the argument that if we did those substitutions, NH2, that third one is there so that we could remove one of those hydrogens. Let's call it green or blue. And that once we removed that, we'd then have a negative nitrogen that could act as a nucleophile in the next step. So looking at the next step, that iodine is, as I completely erase it, that iodine is going to withdraw electrons from that carbon, making that carbon very positive. Okay, so the end result of that first step should give us something nucleophilic to react with that positive. So maybe that last one of NH2 is to go through and act as a base to remove one of those hydrogens. Well, which hydrogen should it remove? Since there's only 3 equivalents, it can't remove both. It would only remove one of them. Okay? So that becomes challenging. So maybe we could look at our answer choices and hope that would help guide us along. if that was the case, we'd remove one of those hydrogens and we'd put a CH3 on one of our nitrogens. Did that happen? A shows the double substitution, fantastic, but then it showed the substitution happen again to both positions. We just said we only have enough to react once, so that doesn't make sense. B does have it react, but now we're only explaining the reason for 2 NH2s, not 3, because note we didn't do that substitution. So that one doesn't make sense. C is the same issue as the one above, which then means D, the thing that looks like none of the others, has to be the remaining choice. So what the F? How is that one a valid choice? Okay, well, what we pushed was looking at the nucleophile aspect. Maybe we shouldn't be looking at a nucleophile, we should be looking at it as a base. If it's a base, I need to be looking for acidic hydrogens. Hydrogens that say beta positions to leaving groups. I could go through and remove those hydrogens. If I remove one set of hydrogen, I could form the pi bond there. If I remove the other hydrogen, I could form yet another pi bond. Okay, and I would have a triple bond. That triple bond doesn't have electrons, and if we go through and look at the end, it doesn't disappear. So why would I have the third equivalent of base? Well, remember, looking at our second step, we need a negative charge. I don't have a negative charge in this structure yet, till I remember there's an acidic hydrogen on that tail end. That base comes in, removes that hydrogen, giving me a negative triple bond. That negative triple bond can now act as a nucleophile. Tack up there, we drop on that last CH3, and there's the rest of that piece. Hard question? Absolutely. Is this going to be what you're expected to do in OChem 2? And then some. Typically what will happen in OChem 2 is you won't be given the reagents. You may be given the reactant and the product and told what are the reagents to do this. You may be given the product and told what's the starting material to get there. Okay, so all of those kind of connections you have to be thinking about. Notice a lot of the stuff that we've got drawn up there are charges. And we're addressing those definitions of nucleophiles and bases and electrophiles, and those things constantly have to cycle through our analysis. When you move into OChem 2, if you move into OChem 2 with me, we do address the ability for these of nitrogen acting as a nucleophile. It doesn't. Okay. Synthetically, nitrogen is awful as a nucleophile. It's a bad idea. So we don't use it as a nucleophile. Which means if we see it, what is it acting as? A base. And if you run the base reaction, it makes a little bit more sense. And you might be like, there's no way in hell I would have ever thought of that. That is potentially true. That is also why one of your other questions that we've walked through already today brought in that negative triple bond. That question was selected to help try and guide you to be thinking about this, probably subconsciously, to get you to that negative triple bond. That was the hope. Doesn't mean it did, but it was selected to help kind of subconsciously push that. Questions?
Yeah, Mike.
So, mechanism decisions. We've walked through something similar to this before, starting with the substrate. If we go through in color code, we're looking at secondary. Nucleophile is hidden behind that metal, but it's Br minus. That minus is suggesting that we're looking at a strong nucleophile. And then the last bit of information we're given is DMSO as our solvent. I'm going to try my best to remember, but because it's open note, I have an out there that those should be getting written in as structures for our solvent. So what I may try and do is put at the very beginning under the instructions with the periodic table a commonly used abbreviations and provide some structures. So DMSO is typically a solvent. There's our dimethyl sulfoxide. As a DMSO, or that with that structure, we should see that that is polar but aprotic. Why all this referencing? The secondary substrate says that we can do SN1, SN2, E1, and E2, which means ultimately that was a useless thing to look at. The strong Br- would be suggesting 2 type. So we'd be going SN if we thought it was a nucleophile, or E if we thought it was a base. Can Br- act as a base? No, because that would be the formation of HBr, and that's a strong acid. Okay, which we now have a bit of evidence that we're pushing SN2. If we go through to look at the solvent, a polar aprotic solvent leads us to an SN2 mechanism. Oh, and that's what the question was asking. Okay, so there we go. We're looking at SN2 as the end result. And that would be all of the thought process, even the dead end in looking at the substrate. Questions on that? $71.15. Whoops. Not the button I wanted. E1 mechanism. So 1 type should be telling us carbocations. So we could go through and look to see if we have carbocations. There's no carbocations, which suggests a bad, carbocation, so both of those are possibles. If we go through and look at D, just because it's the bottom and easiest, we're taking electrons, Br-, and we're sharing them with that carbocation, which means we're forming, E1, elimination, form a pi bond. In D, we're forming a sigma bond. D would be a substitution, so that one's not right. If we look at C, we may have bromine pulling off a hydrogen. We may not like that, but what are those electrons doing? Those are then going into forming electrons in a pi bond. That's doing an elimination. That's making a pi bond. That one looks good. So that one is an elimination, and it also has the carbocation, which suggests E1. D is coming from an SN1, because we have the carbocation. B has problems, because you have the pi bond attacking a negative, okay, which doesn't make sense. Okay, that's electron to electron. So that's a bad mechanistic arrow. So that's bad all around. A, we have the base coming in, removing a hydrogen, forming a pi bond, kicking out the leaving group, but it's all happening at once. That would be an E2, and you were asked for an E1. You may not have liked C because you're saying Br- pull off the hydrogen. I don't like that either. It doesn't mean it's not typically shown, or not sometimes shown. When I go through and do the eliminations, particularly with halogens like this, E1s, I just don't show the acid-base step. I just show it that way. And just say the hydrogen just comes off. That tends to freak people out because they're like, what? Well, what reacted with the hydrogen? Something basic reacted with the hydrogen. Something. We don't really care necessarily what that was. And it could have just as easily been heat. Heat was there enough to activate and remove the hydrogen. Questions on that? (36). We're looking for electron rich. Electron rich should be a red flag of looking for something negative. So we might immediately jump through and be like, well, that sucks. There's nothing obviously negative. The easiest way to hide a negative would be to hide it behind something positive. The thing that would be most likely positive would be a metal. So if we dig through here for a metal, there's magnesium. That's the only one with a metal. There it is. This is CH3, CH2 negative, MgBr, Mg plus 2, Br minus. That metal to negative gets you your electron rich. This can be a tricky question for looking at some of the others. Some people will go through and say, well, another possibility for a positive could be a hydrogen. The problem with looking for that as a hydrogen is that if we go through and look at the reactivity here, while that hydrogen is positive, making this oxygen negative, does that make the oxygen electron rich? And so what that's really referencing is its reactivity, its chemistry. If we look at the chemistry of this molecule, how does it act? Well, that's a carboxylic acid. Acids accept electrons. They aren't electron rich. It's reacting as H+. It's not reacting as O-. When we go up to A as an answer choice, the Mg is a plus, but when we look at how that molecule reacts, the magnesium is a spectator ion. It doesn't do anything. Okay, so that's why the metal is really a non-existent partner in this reaction, and you're really looking at the negative carbon. That particular reagent you will see in second semester. It's known as a Grignard reagent. It gets named because we have a negative carbon. It's rare to get negative carbons. Questions on that one? Three. So the question that you're asking is coming from Unit 4, and so that's good because you're out in front of the game. When we're looking at that particular reaction that's shown on deciding should you get a carboxylic acid or not, what it comes down to is looking at your starting pi bond. That starting pi bond will have 4 things connected to it. If one of those things is a hydrogen, then yes, you have a carboxylic acid because you can oxidize that further. And so in this particular case that's shown here, there is a hydrogen, so it will form that carboxylic acid. But what happens? What happens if instead of that being a hydrogen, we made that a CH3? We're still going to do our stretching. So for those of you that aren't aware of it, that's okay. Don't stress too much, but here's the kind of cheat behind it. For this particular reaction, we can stretch the pi bond, erase the middle out, replace it with oxygens, and then we have to evaluate, because everything else stays the same, then you go through and you look at those carbons and decide, do they have hydrogens? If there's a hydrogen connected to that carbon, because that's where all the chemistry happened, that's why we're focusing in there. If there's a hydrogen connected there, then you put on another oxygen. You insert another oxygen instead of the hydrogen, and that's how you would get to the carboxylic acid. If in the case of the newly modified structure, those are CH3s, well, now there's no extra hydrogen there, which means you can't oxidize and it stops at the ketone.
Okay.
To start with an alkene that is tetrasubstituted is rare, which is why most of the questions you're seeing, you are resulting in a carboxylic acid. Okay? And that's why in the example that I started with, the structure that I picked to start with had a free-floating hydrogen on it so that you could see that extra chemistry coming in.
Okay, so just look for the hydrogen basically that's on there. If it's not there, then you're stuck with the carbon or the ketone.
Yes. Yes.
Doesn't matter on heat really, or coldness of it.
So
Does
the it's not so much the heat and cold. The heat is typically there because you're trying to push the oxidation as far as you can.
Okay.
Sometimes that shows up. A lot of the temperature has to do with the activity of the individual reagent. If the reagents themselves, the carbon structure, isn't reactive, then oftentimes you see heat. usually you need heat. That doesn't mean always you do. So when you're seeing questions pop up in, say, Smart Work or online, sometimes you'll see heat, sometimes you won't, because literally the reagents changed how we needed to run the reaction. So heat is a common signal for pushing the full oxidation. The other thing to look for is the concentration. If it is concentrated, you need to oxidize as much as you can. Okay? If it is not, where's the thing? There it is. If it is not concentrated, you see dilute or DIL commonly, you don't fully oxidize. In fact, you don't even cleave. You stop at the diol. So it's the combination of cold dilute and heat concentrated. I have always seen heat associated with the concentrated, and so I've only keyed off on that. It is interesting that it doesn't have to be hot, but that's really going to come back to the carbon structure.
Okay, and then so with the dilute, is it safe to say that because the permanganate's starting to act like the osmate oxide? I think that's how you say that, right?
Yeah.
So if it's dilute, it's going to basically do the same thing as the osmate?
Yes.
Okay.
Yep.
So osmate's the same thing?
Yep.
Okay. Just memorize that then, basically?
Yeah. And the osmate one, I think, is kind of irritating because of that step 2, which if you've been watching the videos, you've probably heard me reference it. The step 2 sometimes shows up, sometimes doesn't, and I find that particularly irritating.
Mm-hmm. And you can't do the stretching won't appear for osmate, right? It's just the permanganate that the stretching you can do the cheat for?
For cleavage. Yeah. So if you were doing permanganate dilute, you aren't cleaving it, so you can't do the stretch of the double bond because it's not a cleavage. It's only when you do cleavage can you stretch the double bond because that's the breaking of it.
Gotcha.
Does that work?
Yeah, sounds good.
Hi. Masochist. Identify the reagents that will complete the following reaction. So if we go through and look at this reaction, whoops, that was an eraser. We're switching out the OH for the BR, so we're definitely doing a substitution. Because it's happening at a primary substrate, we're doing an SN2. Because we're running SN2, we would lead to being a strong nucleophile. All of these give us strong nucleophiles, so all could potentially work. Before we get too excited and jump straight to that, let's just run through our mechanism. It attacks, it breaks, and we would eject OH minus. Is OH minus a good leaving group? That is unfortunately a bad leaving group. If we go back to our leaving group abilities, if they are strong bases, they are bad leaving groups. Hydroxide is our characteristic strong base, our definition of it, which means just throwing in Br minus doesn't work because hydroxide's a bad leaving group. So to get this reaction to run, I need to make sure that OH is actually a good leaving group first. How do I make sure it's a good leaving group first? Well, I need to attach something to it. I would need to make sure that that's positive, so one of those pairs of electrons needs to be involved in a bond somewhere else. The easiest place to bond that up would be with a hydrogen, which means I also need a positive hydrogen, HBr. I need to be adding a strong acid to make the leaving group good so that the nucleophile can come in and do the backside attack. Questions? That timing-wise, 82-ish. Hopefully it doesn't bite me. The answer is D, but we'll see what happens. So, we want to predict the final product of B. So, what happened along the way? We've got some useful information told to us that we're SN2s. Realize that we do not have to tell you that these are SN2s. You would have to be able to look at your reagents to be able to figure that out. We would know that they would need to follow SN2 reactions because we're looking at strong nucleophiles because they're negatively charged. Okay, so what happens? If it's SN2, the complication is we get inversion of stereochemistry. So when we go through and run the reaction, we would end up with bromine being dashed from our first result. If we did the next one, we would get inversion again, which would mean fluorine being wedged. And if we go through and look at our answers, of course I need to see D, because why not? We also have to realize that that other position there didn't change. So that needs to stay wedged through this whole process. So at the end result, we need the fluorine and the methyl to be on the same side. A would be the result of doing a rearrangement. The rearrangement only makes sense, that says rearrangement, if we did SN1. We were told to do SN2, so that doesn't make sense. If we look at B, B has the fluorine dashed and the CH3 wedged, which doesn't make sense because we said they should both be wedged. If we go through, there's C, they're both wedged. Now I'm going to have to undo this because it's looking like C is our valid answer. And let's scroll and see what D gave us as an option. D gave us that fluorine wedged again, trying to set us up with saying, what do we see? That we want that wedged, but then forgetting that that other position had nothing happen to it. The chemistry stays the same. Okay. So questions on 27? Does that make sense? Okay. I don't know if I gave a time, but right now it's 86, so maybe 83, 84. So before we can get into 22, got to answer 21. In 21, the following rate law, we are given one species, which means we're looking at a unimolecular reaction. So SN1 could work. SN2 do not. Neither does E2. D gives us SN1 and E1. We aren't given any information about whether we have a nucleophile or base. The rate law for SN1 and E1 is the same, which means our answer comes out as D because it's unimolecular. When we look at the next question, it's then saying that that rate expression seems odd for that mechanism. Okay, and we might say, well, why? Well, let's push. Okay, so before we even look at answer choices, why might it seem odd? We're given the mechanism for this particular substrate. And if we look at that substrate, it is a primary substrate. Where the leaving group is connected to only one other carbon. A primary substrate would suggest only SN2 mechanisms, and yet the answer would be SN1. Okay? Well, maybe we were wrong. Maybe it should have been SN2. But if it was SN2, we would have also expected to see the concentration of the nucleophile in our rate law, and we did not. Okay? Which means it couldn't have been SN2. So why is this reaction or rate law odd? That substrate says we should be doing SN2, not a one-type mechanism. So if we go through and look at our answer choice, our rates are never dependent solely on the nucleophile. That's not true. Rates are never unimolecular. Also not true. The substrate would likely undergo SN2. Yeah, it's a primary substrate. That should do an SN2 reaction, not SN1 or E1. And then we get the there's nothing odd about it. So you're really whittled down to a 50-50 on deciding do you know to look for those structural details in your reactions. Questions? So if we're looking at the reagents to complete the reaction, this is one that is strictly a memorization for the record. Knowing how to transition from the triple bond to the acetylide, that reagent is very specific and it only works in certain circumstances. Okay, so if we go through, you should hopefully be able to eliminate answer choice B as an answer, because that would be Br minus, and Br minus is not a good base. Okay, so if we look at the reaction, what's happening is you're removing a hydrogen, right? So this is an acid-base reaction. We could look at using OH. If OH was used, we'd then be making H2O, and we'd be trying to decide, is that a valid reagent to go through and use? Because we have other negative species, we can't do it. We can't say that's the answer because it's a base. We have to evaluate on a deeper level. In that deeper level, we could try and make arguments about which one's more stable as a negative, the oxygen or the carbon. And that, unfortunately, for the triple bond, is going to end in a dead end. It's not going to work out nicely for us. You'll end up finding that none of these answers work. Okay, so we're going to have to push deeper on this, and this is where I would recommend memorization. The question is going to become, what do you want to memorize? The easiest thing to go through and memorize would be that if you want to deprotonate in a triple bond, removing that hydrogen, you need a base that is a negative nitrogen or stronger as a base. Nitrogen is a stronger base than the oxygen. Why is the nitrogen a stronger base than the oxygen? Because the nitrogen is less electronegative. Because it is less electronegative, it is willing to share those electrons better than the oxygen, which makes the nitrogen a stronger base. Okay, so with that memorization, the answer is D. Okay, if instead we memorized pKa's, we could evaluate the pKa's. Water's pKa is, sig fig's going to make it 16. The pKa for the acetylene or acetylene is 25. That equilibrium heavily favors the reactant, meaning the reaction doesn't run. Okay? If we move to the T-butoxide, it's not going to be much different. It's still a negative oxygen, it's still a negative oxygen, and then we're still looking at an alcohol. I think this one becomes slightly, I always get tripped up on this one, slightly more acidic. It's still heavily going to favor the reactants, so it doesn't work out. When we go through and move the negative nitrogen, when we go through and look at its pKa, the pKa there is about, not 9, 35. Okay, because the pKa is higher, our products are favored and the reaction progresses forwards. The triple bond is an exceptionally valuable reagent to have as a negative because it is hard to get a negative carbon. Carbon can't stabilize negative charges well, so anytime we can make a negative carbon, you should be really spending some time to memorize that reagent. The acetylide is the common one. You get it by reacting it with a very strong base. What we'll learn, or what I'll reference it as in second semester, is a stupidly strong base. The base needs to be more basic, equal to or more basic than a nitrogen. Does that answer your question? So for 39, we're looking at unaffected by. Okay. And so if we're referencing that, we're talking about our rate. And if it's unaffected, this species does not show up in our rate law. Okay, so what is that species? We're talking about hydroxide. Okay, hydroxide being a strong, because it's negatively charged, could act as a nucleophile or as a base. Because I don't want it showing up in the rate law, okay, as a nucleophile, I don't want SN2. Since I also don't want it showing up in my rate law, I don't want it acting as a base, so I don't want to see E2. Because it's a base, it could also potentially act in an acid-base situation, so I also don't want to see an acid-base reaction. So if we go through and look at our rates, SN1 is the only one that fits the bill. Both SN2 and E2 use hydroxide, In SN2, it's used as a nucleophile. In E2, it's used as a base. And in the acid base, it's used as a base there. Questions? I don't know if I gave you a time. 91-ish. So this is... Oh, come on, you stupid eraser. This is really tipping off on anti, and this question has been a common misconception that for whatever reason I decided to write a question about it this semester. People are mislabeling what anti means. When we're talking about anti, A and B are anti to each other because they're on opposite sides of that single sigma bond. Okay? That anti-relationship happens there. If I go through and do a whole bunch of things, A and B aren't anti to each other anymore. That anti is referencing very particularly about the Newman projection that is at that bond, that one bond away. As soon as you exceed that bond, you're not referencing anti anymore. Okay? That's not a useful representation of it. Okay? So anti is a very close proximity thing. Okay? So if we go through and look at this question, you can see where that trap is really falling in play. A lot of people throughout HB. Why? It's on the opposite side of the structure as the bromine. That's true. It is on the opposite side, aimed the complete opposite direction. It's not anti. Anti is very particularly referring to the Newman projection. So you have to get into that Newman projection. If we're referencing the bromine as part of that Newman projection, we're either setting down the red bond or the blue bond. HB has nothing to do with any of those characteristics. HB, as far as this question is concerned, is a red herring answer, okay, and should not be selected. If we go through, HA is going to be aimed the same direction as the bromine, the same thing as HC. Minimally, what you could do with both HA and HC is eliminate them both as potential answer choices, because if A was correct, then so does C. Okay, because they're the same relationship to each other. So you could eliminate both of those, which then means HD is the only one. HD is the one that is indeed anti to this. How would you get through and really formally go through and show this? Super exciting. Okay. We would have to really go through and draw out the Newman projections to understand that full-on relationship. And yes, this is exceedingly challenging to go through and do, but this is what you would have to do to fully evaluate this. In this case, I'm going to pick... I got to think about it. Be sighting down that bond. Okay. The bromine dash, so aiming down. Okay. To be anti to it, I would need to be up here. Okay. If the bromine was dashed down, that hydrogen would need to be wedged and up. There it is, HD. And hopefully I didn't draw a mirror image. I think I did it right. The methyl technically would be out here. There would be that CH3. HC is here. HA is virtually impossible to draw on there, but it's right there. And then HB is out there. Okay? So yes, it's hard, and I think it's because of the misconception on what anti means. Anti is very, 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 very local. Treat it as local. Okay? Don't be looking long distance across structures. Questions on that? If you wanted to reference this later, we're at minute 99. Oh. The numbers up here, 1, 2, 3, 4, 5, 6, and then kind of numbered sequentially all the way, the rest of the way through. So if we take a look at fractions 1, 2, 3, 4, 5, there's nothing there. Okay, so we don't see anything because when they spotted, nothing showed up, which means those fractions don't have anything in them. Fraction 1 was the very first thing off the column, so that actually makes sense. Okay, we shouldn't see anything coming off the column for fraction 1 because we just put it on the column. Then what happens is compound starts to come out, and that's what we're seeing starting to happen in 6. And you could probably make the argument, it may be just an artifact on my screen, but it looks to me, and I'm in the annotation mode, but it looks to me like there is a little bit of a dot on fraction 5. Okay, so you could make that argument. But let's just go through and say 6. So 6 has something in it. So does 7, 8, 9, 10, all the way up. And as you look through at these, and I'm pointing at the freaking screen, as you go through and look at each of these dots sequentially, what you might notice is it starts to get a little bit fainter towards the end, okay? Which kind of makes sense because your compound's already come out. There's less and less compound trapped in the column, okay? So our compound has come all the way out. We now need to go through and evaluate what's in there. Because we don't know what's in there, theoretically. In this case, I think you were told it's a mixture. Did I tell you? Honestly, don't remember. I think I told you that there's a mixture of 3 things. If this had been an awesome plate or an awesome column, in theory, what we would have seen would have been nothing. Oh, compound starts appearing. Nothing, compound starts appearing. Nothing, compound starts appearing. Okay, running the same numerical sequence. 1, 6. Does that make sense? So you're seeing stuff come off and then nothing's coming off. Why is nothing? Well, because there's space now in between those. Okay. Columns rarely work that cleanly, and you usually end up seeing the blended mess that we've got here. Okay, so what we now need to go through and do is evaluate each of those fractions and decide what's actually in them. Because if we go through and look at fraction 6 and there's 2 spots in there, well, then we might say that the column didn't do a very good job. So we want to go through and test these. The other aspect with our column is the whole point is to get compound off. It's a separation scheme, meaning I get lots of stuff at the end of it. Okay? So I actually want to combine fractions when they're the same compound. This TLC plate doesn't tell me they're the same compound. Okay? All it does is tell me there's something there. So that's where I would have to go through and select which of these I want to run a full TLC plate on. Because I don't know where that division is between A, B, and theoretically C, I'm going to just pick kind of random things. Why random? I can do it in sequence, but that means I run every single plate. It is possible that if I kind of scattershot my plates, that I could find that I don't need to run every single plate. So in this case, I might run 6, 9, 12, 18 and see what the results are. Okay? Because maybe what I'm seeing here is all one compound. Okay? So I'm going to pick some random ones to get kind of a scatter through it and see what I get. When we go through and take a look at the TLC plates that they ran, they picked 7, 10, and 13, okay, on their first try. And we go through and look at that, 7 and 10. 7 and 10 both have one spot at the same RF. Well, if it's at the same RF, what does that mean about the identity of the compound? It's probably the same thing. Do we need to run plates on 8 and 9? Well, 10 has the compound running at, what is that, about 0.5 RF. 7 has a compound at 0.5 RF. 8 and 9 came out in between 7 and 10, which means 8 and 9 have the same compound in them. Okay, so 7 through 10 can now all be combined as a single fraction, and you could evaporate the solvent off to get your pure compound. You've now separated that away from everything else. Should we combine 11 or 12? Well, if we take a look at our TLC plate, I'm kind of assuming you can see the numbers. The next one that they tested was 13. Well, 13 shows 2 compounds. 10 only showed 1. When did that second compound appear? Did that appear in fraction 11? 12, or 13. Since you don't know, we should really leave those out of this combination and run a plate now potentially on those. You'll notice that they didn't do that, okay? And that was probably due to time, okay? If that compound at 0.5 RF was exceptionally valuable, we would have run a full plate on that. But again, in the undergraduate lab, we just have time considerations we have to worry about. So what they then went through and tested was 14, 19, and 21. Why? Well, they wanted to see, did they get separation of the second compound away from the first? And so when we look at fraction 14, you'll only see one spot, okay? Which means, yeah, they did. In this case, when they ran the column, they were able to separate two compounds away from each other. Minimally 7 through 10 are pure one compound, and then 14 through 21 are pure the other compound. So they were actually able to differentiate those. How could we go through and talk about them? You'll notice that I already started to do it. That very first dark one, we were saying the compound with the RF of 0.5. Because they have similar RFs, we can group them together because similar RFs are typical of the identical compounds. Okay? So the RFs become more a way of naming the compound than anything else. You are still using the RF to decide what to combine. For instance, you're not going to combine that's fraction 16, not 14. You're not going to combine fraction 16 with fraction 7 because they have different RF values. Because they're different RF values, they are different compounds. Why do we know that? Because we use the same solvent in both cases to separate these things out. If we start switching the solvent, all bets are off and you can't do anything. Okay? So that was 7 minutes of talking that I think answered your question. So I'm going to pause the video and give you an opportunity to rebut. But I'll do it fast. Success of the experiment is based on multiple layers. One of those layers, did you separate the compounds away from each other? The other one is how much compound did you get back out? Okay? And you get to decide how both of those things contribute to your overall experiment. Okay? For this particular unknown mixture, there were 3 unknowns there. There's a failure on the design of the experiment. One of those compounds doesn't show up on the TLC plate, so you can't evaluate that. Okay? RF values and TLCs and all that become very challenging to deal with. Okay, so we'll walk through it. The higher the RF value, the less polar the compound. Okay? The higher the RF value, the faster it moves through a column. Okay? The lower the RF value, the more polar the compound. The lower RF value means the slower it moves through a compound. Or it moves through a column. That sounds relatively straightforward, so then why would you be getting it backwards? You're getting it backwards because what you're confusing is what happens with solvents. Solvents push your compound and thereby change or create the RF. The more polar solvent will push harder, making all compounds have a higher RF. The less polar solvent will push less hard, will push softer, and have a lower RF value. So you have to be very careful with TLC and RFs to make sure that you're referencing what you're referencing about the RF and polarity. If it's compound and RF, more polar compounds have lower RFs. If it is solvent and RF, more polar solvents generate higher RFs. And I did record that. Gary, if you're using both a polar and nonpolar solvent, we want to use the nonpolar solvent first. So why would you do that? So remember, the polar solvent pushes harder, making all of the RFs higher, which means all compounds move faster through the column. Well, if they move faster through the column, the separation distance between those compounds is going to shrink because they're all going much faster. So you want to use a nonpolar solvent first, because now your nonpolar stuff can move off the column really fast while your polar compounds are still stuck. When you switch to the polar solvent, now the polar compounds will now have an opportunity to move, but your nonpolar stuff has already left the column. So you've given yourself an opportunity to actually allow those other compounds off the column first. Hopefully that makes sense.